Next topic is indexing and BTrees or B plus trees. So for understanding this topic, first of all, we have to understand the disk structure. There are few numerical questions from this topic in GATE. This topic is having more number of questions compared to the number of questions from ER diagrams. Like I told you, more number of questions are there from queries and normalization, that is functional dependencies. More number of questions are there. Then the questions are there from BTrees, B plus trees and transaction processing. Almost equal number of questions. Then the questions are there, very less number of questions are there from ER diagrams. So we'll start with this topic. So for this we have to understand disk organization. I'll explain you disk organization. This is disk structure. These are called as tracks. These are tracks. Concentric circles or the tracks that we see, or strips, circular strips that we see are called as tracks. And this portion is called as sector. So this pie-like pieces, these pieces are called as sectors. We'll number the tracks: track 0, track 1, track 2, right? So this is 0 track, this is first track, and this is second track. Then we'll number sectors. This is 0 sector and this is sector 1. Okay, I'll write S0 to show that this is sector 1, sector 2, sector 3, sector 4. These are the sectors. So a disk is divided into tracks and sector. Each track is having its number and the sector is also having the number. So this is how a disk looks like. This is called as a spindle on which the disk is mounted, and there is a post on which this is disk head. This is head. This is spindle and this is head. Now how the data from disk is accessed, means reading, writing, updating, whatever it is. How the data is accessed is using head. See, the movement of head, the head can move in this direction. The head can move in this direction. So if we imagine head here, then head can move in this direction. So if head is moving in this direction, it will be changing tracks. So head movement will help in changing track. Suppose the head is at some position. Now head is here. Now this can rotate, it can spin. So the spinning of a disk will change the position of a head like this. Head will be still only, but the disk is changing. So the spinning of a disk will change sectors. The spinning of a disk will change sector. Now, how we can access a particular location in a disk? So let us talk about a particular location. See, if we say this particular location, this is called as block. So all these are blocks. All these are blocks. So blocks are formed with the help of tracks and sectors. So what is the block number? This block number is, this is a track 0, this is a track 1, this is a track 1. So track 1 and sector 0, sector 1, sector 2, sector 3. So this block is sectors 3. Track 1, sector 3. Any block on the disk can be accessed with the help of its address. How the address of a track is, address of a block is given. The address of a block is given in terms of a track number and sector number. To access a particular block, let us say this block on a disk, this block has to be accessed, or this block has to be accessed. The block number, that is track number and sector number, should be given. If based on the track number, the head will move. Based on the sector number, this spindle will spin and bring that block right under the head so that head can read that particular block. So that's how the data on the disk is accessed in terms of block. Let us talk about size of block. Size of a block can be anything. It depends on the hard disk. It depends on the disk. So typically we take it as 512 bytes or 1024 bytes. So basically when we study, it depends on the manufacturing, right? But when we study, we say the block takes so many bytes. So let us say 512 bytes. We fix some value and we study it. So we assume that block may be of any one of those sizes or 512 size. So the block size is 512. So the point here is, okay, when a head is positioned upon that particular block, then the head can read the entire block. Head can read the entire block. So at a time, one block of data is read from the disk. Now if you ask, okay, let me say like this. If we talk about main memory is divided in terms of bytes or cells. Memory location. Each byte is having its address. Each byte is having its address. We can access any byte with the help of its address. If I want to access this particular byte, I need its address. And the address is a linear value, that is scalar value, not a vector value, single value address. So usually the addresses of disk start from, addresses of main memory start from 0, this is 1, 2, 3, 4, 5, this is 6, 7, 8, 9, 10, 11, goes on. So if you have 64 kilobytes of memory, then the addresses will be 02655535. These many addresses will be there. So these many bytes are there, and every byte is having its address, and the addresses are starting from 0 onwards. So those are scalar addresses. But on the disk, it's a vector because this is of two values, that is a track and sector. Two values are there. So the address of a block is given in terms of track and sector. Now the question is, the block size is 512 bytes. Block size is 512 bytes. So can't we access a particular byte in this block? No. When the head is positioned, it can read entire block. If you want to access particular block, particular byte, then you have to take offset. So in every block, again we take the similar pattern, that is the addresses start from 0, 1, 2, 3, if you say these are bytes, 4 onwards. So this is nothing but offset. I want to read 4th byte. So entire address will be track 1, sector 3, offset 4. So it means in this particular block, I want to access 4th byte. So this is how a particular byte on a disk is addressable. But usually what happens is, once a head is positioned there, the entire block of memory is transferred into main memory. Right? This is what usually happens. So finally, in this discussion, we understand that the disk is accessed in terms of blocks, not in terms of bytes. If you want to refer a particular byte inside a block, then you have to mention the offset of that particular byte. So what are the possible offsets? If a block size is 512, the possible offset, the range of offset is 0 to 511. Starting from 0 onwards, so last is 511. So total 512 bytes. So the offset can range from 0 to 511. And the track numbers, how many tracks will be there, how many sectors will be there, that depends on the physical properties of a disk. So this is about the memory structure. So disk structure, how the data is stored on the disk. Now, let us come to database, right? This block, okay, let us talk about a file, how a file is stored. If I am storing a file, the file can be anything. It can be a Word file, or it can be a PDF file, or PPT, it can be any file, text file, whatever the file may be, image file, video file, whatever the file may be. So I'll give the name as my.doc, that is document file, Word file. Now the question is, how many bytes, what is the size of this one? Suppose the size of this is 1 kilobytes. 1 kilobyte means how many blocks it requires? Total 512 into 2 is 1024, that is 1 kilobyte. So 512, we require 2 such blocks for storing this particular file. So 2 blocks has to be allocated for this particular file. So let us say that file, my.document, is stored in this block and then consecutive block. This block and consecutive block. Right? This requires 2 blocks. So 2 blocks are allocated, and that entire data of the file is stored in this one. So the file size is 1 kilobytes. Now, usually you might have seen on the system, when you see the listing of a file, that is a directory listing, or folder, when you see all the files, you can see the property, what is the size of a file. So depending on the block size, that many blocks it will be occupying. So you can find out, if you know what is the block size on a disk, then you can find out how many blocks each file is occupying. Now, next. Okay, I'll discuss a little further on this one. So what actually operating system will manage the disk? We programmers or application developers will not directly access disk. We take the help of operating system. So for saving a file or deleting a file or reading a file, we take the help of operating system. So operating system will store a file like this. Then it should know which file is stored in which block. Like there are a number of files on the disk. So which file is stored in which block, what is the starting block, what is the ending block, total how many blocks it is occupying, all that information is stored in one table that is called as file allocation table, FAT. And this FAT is also kept on the disk only again, right? Usually track 0 is used for storing the file allocation table. So that FAT is stored on file allocation table. So, track 0. So FAT will contain the information about the file. So this is one thing. Now, on a disk, we may be storing the files, we may be deleting the files. So the files may be coming in and going out on the disk. So when we want to store a particular file, we may not get 2 blocks consecutively. Consecutively, we may not get 2 blocks. So suppose this is one block and this is another block which is allocated for this particular file. This file is getting these 2 blocks, this block and this block. Okay. So when it is getting these 2 blocks, then a link is kept inside this block to show that next block is here. It means the address of this block. What is the address of this block? Track 2 and sector 6. Track 2, sector 6. This information is kept inside this block. That is nothing but a link to the next block. So the blocks for a file may not be allocated consecutively. It depends on the availability of blocks. So how the sequence of blocks is maintained is with the help of link. A block may contain the address of next block. Alright. So a linked list of blocks is maintained. Right. So definitely after storing the entire data of a file, we need some space for storing the link of next block. Right. If the phi12 is the exact size of this file, exactly 1 kilobytes are required, and phi12 is the exact size of a block, then this entire thing cannot be stored in just 2 blocks. We require some extra space here for storing the link, and when we have taken that much space, then the space is that is gone for address. So that space we require here. So we need extra space. So it may require 3 blocks. So again, this will have a link to this one. This will have a link to this one. So blocks are kept in the form of linked list. So one more fact, important fact about this is every block may have some space required to show the link of next block. That is next block address. So we can call this as a block address. So this is block address. Point. When I said that, okay, I'll just make a change here. Suppose this files require 1200 bytes. Then phi12 into 2 is 1024 plus remaining is 176 bytes are remaining. So this will go into 2 blocks and this will go into 1 block, and still in these 3 blocks we require some extra space for address also. So if we say 10 bytes for address, if we say this address is taking 10 bytes, so total 30 bytes more we require. Right. So let me explain one point here, that one block is occupied, second block is occupied, and third block I have just increased the size of the file little bit to show you that remaining 176 bytes or more will be occupied here. So remaining portion of a block is left empty. What about that? So that will not be used by any other file. That belongs to this particular file only. So in this way some memory may be wasted on the disk. So if we keep very large size blocks, then a lot of memory may be wasted. Only only 176 bytes it is using, so remaining bytes will be wasted. So you can say that the better sizes, better to keep the blocks in the smaller sizes so that the memory is not wasted, because this block cannot be allocated for 2 files. If you are allocating for another file, this much space is allocated for another file, then in the file allocation table you require track number, sector number plus offset also for finding the address of a particular file. So usually this is not done. Only the file addresses are kept in the form of tracks and sectors. So the important facts for our topic, that is in DBMS, is that the block part, right, and the address inside the block. This is second point useful for us. And the third point that is useful for us is entire block is given for one particular file. It is not shared between 2 files, right? And one more point important is block are having some sizes. Blocks are of some sizes, right? Whatever the size may be. There are gate questions on this one. So you should know the size. He will give the size. You don't have to assume the size. There is no standard size for it. So size will be given. So the size of a block will be there. And the size of file, like we will see further, what type of data will be stored. So this type of discussion is also there. So how the tracks and sectors are accessed by a head, I have shown you that movement of the head will help in accessing tracks, and the movement of spindle will help in accessing sectors. Now when we come to databases, our database may be having tables, and the tables are stored on the disk. So we see how the tables are stored on the disk. So a table will contain nothing but collection of records. Let us see. I am taking one schema, account, having account number, branch name, balance. This example I am taking. Suppose this is one table, a relation. Now what is the size of the relation? Account number, let us say this is taking 8 bytes. Branch name taking 12 bytes. And balance is taking 10 bytes. So what is the size of each record? Size of each record is 38 bytes. Size of record is 38 byte. Now when we see some table, instance of this one, account number, branch name and balance. This is one record, next, goes on. Now let us see. This is a relation example table, and this is the schema of a table, and this is the size of each record. So it means if I write one account number 20 and the branch name is Mumbai and the balance is 500, so I'm not writing bigger figures. This is the balance. So this is one record. So how much space it is occupying? 38 bytes of memory space it is occupying, right? Now let us see some numerical thing. If this relation account is having 100 records, right? Now first we will find out how many records per block? How many records per block? If 38 is the size, then if 512 is the size, then 38. So how much it will be? 3. Okay. 10 times and 140. 13 almost. Yeah. Hmm. 13 or 14. So if I take exact value, I'll just check it. .47 we are getting. So it means this is 0.47. So leave it. We can store how many blocks, how many records per block? We can store 13 blocks per record, 13 records per block. And some space will be remaining. Some space will be remaining. If I take 38 so total how many bytes it will be occupying? 594 bytes it will be occupying. Remaining bytes are useless. Remaining bytes are useless. So in a particular block, so total 13 records will be there. So if I start counting from 0, 1, 2, 2, last is 12, and this space is free. So usually what happens is, you will have some space left over in a block, right? I have not taken a figure that is exactly dividing 512. If I take that, then the space will not be left over, right? So I have taken this example. So in this one, so total 13 records are kept and some space is left. I just now have shown you that in every block you may require some space left over for having a pointer. So yes, remaining bytes of memory is can be used for block address, that is showing the address of the next block. Now next, so what we have seen, how many records can be stored per block? So 13 records can be stored per block. Now the question is, 100 records can be stored in how many blocks? 100 records can be stored in how many blocks? So each block can store 13 records. So 100 divided by 13. So 100 divided by 13 gives exact value what? 7.69. So it means 7 plus block we require. 7 plus blocks. So total 8 blocks are required. 7 plus blocks are required. So that is 8 blocks. See, the 8th block is not fully filled. Some space is left over still. So it means it will be having less number of records there, not all 13 records. So this type of numerical are useful. This type of questions are important. So let us repeat once again. The size of the record is so and so. First we found out how many records can be stored per block. So 512, if we assume the size, then 512 by 38 gives us 13. So 13 records can be stored per block. Then for storing 100 records of this particular table, how many blocks are required? Total how many blocks are required? 100 records, how many blocks are required? So 100 divided by 13. So gives what? 8 blocks. So this entire table can be stored in 8 blocks. Now let us move ahead, move to the next. And that's all about the blocks and the records. So these are the few records I have. Now let us move to the next topic. Let us talk about indexing. See, in a relation, in a table, if you have to search for the data, then you have to select a key that is called as search key. It is called as search key. So search key is different and primary key is different. Right? Primary key means it must be unique in a relation. Now you can say in this table account numbers are primary key. Right? But the search key need not be a primary key. Search key need not be a primary key. Suppose I want to search the records that all the accounts that belongs to Mumbai branch. So if I say that, then what I am giving the search key as? I am giving search key as Mumbai. So that is branch name. So search key is not account number, it is branch name. So we can search the records based on any attribute, not necessarily be a primary key. Alright. Now, the thing is, how you search these records more oftenly? I search mostly based on the branch name, suppose. Then my search key, frequent search key is branch name. Even I can search them using account number also. Right? I can search based on balances also. All those accounts whose balances are exactly 500, I can search like that also. So searching can be done on any one of the attribute. Right? So I can select any one of the key, any one of the attribute or set of attributes together as a search key. Right? So suppose I am saying that most often I suppose I search based on branch name. Then This is sufficient. Now let us see. This is my relation. This is my table. I am showing only few. You can see that I have arranged the records in the sorted order, right? Based on the branch name. They are sorted based on the branch name. Then a file that is meant for storing a table and the records are arranged based on some search key. They are sorted based on search key. Then we say this is a sequential file. This is a sequential file or sequentially ordered file. So when the records are arranged in the sorted order based upon some search key or some key, then we say it is a sequential file or ordered sequential file. Ordered sequential file. See, now the question here is, suppose I am inserting a new record that belongs to Delhi and its balance is 800. Then when I inserted this record, do you think I should sort the entire records again, once again? No, this is not practical on the disk. There may be hundreds or thousands of records. For every insertion, we may not sort them again. Then how to maintain the order? So for maintaining the order, we can maintain the address of the records here. We can maintain the addresses of the records here. See, this is address, or you can say pointer. I have shown you how you can refer to a particular byte inside a block, that is using offset. So you can use offset, that is a track number, sector number plus offset you can use and store the address here. So you can show that I'm not writing the addresses, I am showing that this is pointing to this one and this is pointing to this one. That's all. This was the end. I have inserted this newly. I'll show you how to insert this. So this is the end. So skip this one. This is not there. So how the order of the record is maintained, how this ordering is done. The ordering is done with the help of pointers. So along with inside a record, along with the data, we should also have a pointer. So if this pointer is of some 12 bytes, so it required 12 bytes extra, plus 12 bytes extra, because each record will be having a pointer to the next record also. So in ordered sequential file, apart from the size of a schema, you need extra bytes for having a pointer. So if you organize the file like this, then we call it as ordered sequential file or sequential file. Right? Now the question is, if I am inserting new record that is for Delhi, then this last record, Delhi 700, this should point on this newly inserted record, and this should point on next record. This is like linked list. When you insert a new node in between two nodes in a linked list, two nodes are there, you want to insert something here, then this should point on this one and this should be pointing on this one. This is how you can insert a new node in between. So same way we have inserted a new record in between. So this should come here. Now you can see that we are getting the order. See this Bhopal record, next record is Bhopal again, next is a Delhi, sorted order, then this one, then this one. Then after this record, 18th record, the next record is a record with account number 30, and the next record is this Hyderabad record with account number 12. So we are maintaining an order. So ordered sequential files can be maintained by sorting the records based on some search key. This is one possibility. Second possibility is we can maintain the link through. So we can maintain their order through link pointers. This is about an ordered sequential file. If Now, next we move ahead. If you are frequently searching in this one, suppose I am searching for records that belongs to Hyderabad, then do I have to access the records of Bhopal, then Delhi, then I should come to Hyderabad, or directly I can access the records of Hyderabad? If I access this file, then I may be reading, when I want to access, when I am searching, then I may be starting from here, definitely, right? I read this one, then this one, then this one. I am searching for Hyderabad records. So here I got Hyderabad records. So I have to go through all these records, then only I can reach here. So if there are some 100 records, I am accessing last record, then I should access all 100 records, then only I can reach it if I am searching for that one. Right? Now, if the search is more frequent on this one, one thing is you have ordered it. Now, to make the search faster, you can add an index. Now, index will contain, index will contain branch name and pointer, that is link. This is our search key, right? So first is Bhopal. Here the Bhopal is starting. Delhi. Here Delhi is starting. Hyderabad. Here Hyderabad is starting. So we can maintain an index. That index will contain the search keys and pointers to the records, right? So here I have to give name to this one, like I told you that this is a pointer to this record. So we call them as a record pointer. This is not block, this is record, next record. And what these are, this is search key. So what is this? These are record pointers. These are record pointers. We can have an index on a key, search key. Now, if you have an index on a search key, and that search key is defining the sequential ordering of a file, then we call this index as primary index. This index is called as primary index. All right. Now, here we see, as I told you, search key need not be a primary key. So there are more than one records with Bhopal. So this Bhopal search key is pointing on the first record. Once you reach there, you can access all the records that belongs to Bhopal. Right? Once you reach Delhi, you can access all the records to Delhi. So you can access all the records from this pointer till this pointer, till before this pointer. So when you have these two addresses, you can access all the records between these two pointers that belongs to that particular search key. Now if I have to access Hyderabad, I don't have to go through all the records and then reach Hyderabad. I can search in the index for Hyderabad. So I don't have to search in the table, I have to search in the index, right? Search for the index and pick up a pointer and access that particular record. All right. So the benefit of index is you can search a particular record faster. How it is faster? See, if you are accessing the records, if you are accessing the table, not the index, and you are searching for Hyderabad, then if you reach here, till he reach here, how many records you are accessing? 1, 2, 3, 4, 5, 6, 7. So total 7 records you are accessing. So each record size is how much? Like I told you here, this is 50 bytes now. So 7 into 50. So you are accessing 350 bytes, right? So 350 bytes of data you are accessing to get the records of Hyderabad. But if you use index, you may be accessing this index entry. All these are entries. So total how many entries you may be accessing? 3 entries. Then you are accessing the records of Hyderabad. So the amount of data you are accessing to fetch particular record is less. So the time for searching is less. Right? You don't have to go through the records which doesn't belong to that particular search key. Now, next question here. So we can talk about index, and we see what questions can be framed from there. See, what is the size of the index? Size of index entry. Size of index entry. So what are the things it is having? Search key. Search key. How much was the search key? 20 bytes. Right? And how much is the pointer? That is a record pointer. Record pointer, I was telling you here, I said that it is taking 12 bytes extra, so I have taken this one. So now, total how many bytes? 32 bytes. 32 bytes. So size of each entry is 32 bytes. Right? Size of each entry is 32 bytes. Now, in a particular block, how many index entries per block? How many index entries per block? So 512 divided by 32, we got 16 entries per block. See, just now you saw the size of the record is total 50 bytes we saw, and this is 32. It's not a big difference. The reason why we are not getting a big difference, because who is of maximum size here? Branch name, that is 20, and that same I have taken as a search key here, right? As an example, this is an example I have taken. So in this example, branch name is 20, and here also I have taken branch name only. So that is a 20 size. So that's why it's almost nearer to 50. So it is, you can say 75% of that, right? Or 80%. So 75 to 80% of the memory it is consuming. So 25, around 20% is reduced. That much is reduced. So how many blocks entries, how many entries I can have in a particular block is 16. If you remember, how many entries were possible here? 13 records were possible in a single block. But now 16 entries are possible. So it is more, little more, not much more. So I am taking only 3 fields here. Imagine there are many fields here and the size of the record is too high. Then I am storing only key here. This will be too less compared to a record. Okay. So the figures that we are getting are not making much difference here. But you should understand the concept here. So not go based on the figures. So how many record entries we can have? 16 per block. So now, see, to access a particular record, how many blocks I have to access? I have to access one block from the index, one or more blocks from the index, and then take the address and come to this particular block. So this gives the address of this one. So it will have the pointer to this block where these entries are kept, right? So total 2 block of access I can reach here. Accessing index, searching in the index, then directly coming to this block. But if I directly search in a relation, suppose this entries are somewhere down, then I may have to access many blocks and reach there. Alright. So if you check here, total how many bytes I am accessing? I am accessing, this is 20 plus 12 I have taken, and that's 20 plus 12, 20 plus 12, right? 32. So 32 into how much? 3. These many bytes. Then next, I am accessing these two. So 50 into 2, that is 100. So total 196 bytes I am accessing to find out the records that belongs to Hyderabad. Right? So 3 entries, that is Hyderabad is the last one here. 3 entries from here, so total 96 bytes, and the 2 entries from here, that is 100 bytes. So total 196 bytes I am accessing to access these records. Otherwise, if I directly access table, then these are 7 records total, 1, 2, 3, 4, 5, 6, 7, including all Hyderabad records. So 50 into 7. So I was accessing 350. I am measuring bytes directly, not just records. I am showing bytes. So instead of accessing 350 bytes, I am accessing just 196 bytes. Right? So almost 50%, you can say, is reduction. So that's how index will help in accessing the records faster. So this is a ordered sequential file, that is a table, and this is index upon the key on which it is sequentially ordered. So this is called as primary index. Now there are 2 types of primary index. One is dense index, next is sparse index. There are 2 types of primary indexes.